So the next speaker is Quan Liu, who will talk about highly ordered PCBM nanomorphology for burn-in free and long lifetime polymer photovoltaic cells.
From ICFO. So today I'm going to talk about the highly ordered PCBM nanomorphology for burn-in free and long lifetime polymer photovoltaic cells. First of all, I'd like to introduce the photoactive materials I use for my work. So PTB7TH, also called PCA10, is one of the most efficient donor materials for OP cells. These materials, combined with PCBM furan acceptor, can offer the single junction solar cells around 10% efficiency. However, these materials have low mobility. This limited the optimal active layer thickness around 100 nanometer. So to further enhance light harvesting without sacrificing the device fill factor and the VOC, we here use a one-dimensional photo management strategy. To be specific, we use a two resonance tapping cavity to improve the PCA10 PCBM solar cells. Here we show the compute electrical field amplitude inside the cavity. Obviously, here two resonance. This resonance is a typical silver mechanical cavity layer. So normally people replace this resonance. But here we also observe another resonance at a short wavelength from 400 to 500 nanometer. This is from titanium oxide dielectrical cavity layer. This is different from the common belief titanium oxide is an anti-reflection coating for this multi-layer transparent electrode. Actually, it's not the case. It has the resonance here. But this resonance is going to disappear when we increase the thickness of silver. And in a rare case, normally the silver between 7 to 13 nanometers. In the middle range, the two resonances are smeared into a big broadband resonance. So that's why we call this cavity is a two resonance tapping cavity. Then we fill this cavity with PCA10 photoactive material, and we measure the enhanced external quantum efficiency compared to ITO reference cells. Using TRTC concept, we gain more than 2 milliamps per square centimeter photocurrent compared to ITO reference cells. And we will say the VOC and the fill factor doesn't affect. So by this approach, we can improve the PCA10 solar cells from 9.6% to above 11%. Also, this concept can be applied to flexible solar cells because the silver has excellent bending stability compared to ITO electrode. Okay, and then here we also change to other blends, and then we can achieve very high efficiency for the flexible solar cells with good mechanical stability. Okay, let's move to the stability part. PCA10, PCBM solar cells has good efficiency, but their stability is far lag behind. It's commonly believed that, okay, PCA10, this material is not stable. It's because, actually it is, because it can be easily oxidated in air under emulsion. But if we encapsulate the blends inside the glove box before doing these measurements, we observe this material can be fairly stable. This is very interesting. So that means these materials can be intrinsically stable in the atmosphere. And the long-term lifetime with this material also could be achieved. So even though we remove the oxygen, we still observe a fast burn-in loss for the encapsulated solar cells. So in the past, people have several explanations for this burn-in. For example, the people talk about the trap states, the morphology instability, and also some materials degradation or additive and so on. But it's still unclear what happened in the solar cells. It's degrading so fast. under the sunlight. Okay, here in this talk, I'm going to first to analyze the sunlight-induced burn-in mechanism, and also I use a method to overcome this burn-in and to achieve super long lifetime solar cells. Firstly, I studied the UV cutoff filter dependent photostability for these materials. Here we use different filters, and you can see if we use a filter with 370 nanometer, the burn-in is significantly suppressed compared to without using 320 nanometer filter. So that means the photons below 370 is the main contributor for this degradation. This degradation curve can be well fitted with this two exponential decay function. And A1, we can consider as the degree of the burn-in loss. Okay, so we also plot A1 as a function of the wavelength of cut-off filters. So here you can observe there's a sharp transition from 320 to 370 to 370. So that means the photons below, the high energy photons, especially below 370, is the main killer for these PCA10 solar cells. So afterwards, we study the evolution of the EQE and the electron-only device of on the solar emulsion. And we can observe that PCBM, this range is a PCBM, is degraded much faster than the polymer range. And the electron mobility also decreases a lot. Here we didn't show, actually the whole mobility doesn't affect too much. So from these results, we can say the UV photons mainly damage the PCBM nanodomains. Okay, this are from the experiment, we have this conclusion. And then, actually I want to know what happened. So I try the morphology measurement for standard AFM or SEM or GRXRD. So I cannot detect the difference before and after emulation of the samples. So now I think about try to understand why. So then here is the setup of the transabsorption we made in our lab. So we pump this PCBM, PCA10 PCBM active film with 382 UV photons. And then interestingly, we observed this PCBM has super long lifetime compared to red curve. The red curve is a typical singular to singular transition lifetime, okay? It's like 200 picoseconds. But a PCBM, it's more or less like the triplet. So that's why then we try to propose a mechanism to explain the burn-in for this material. So when we shine in the light to the active layer, the PCBM absorbs the photons, and the exciton created in the PCBM phase will move to the interface between the polymer and the fluorine, and then they will access an intermolecular charge transstate. Okay, so this S1, S2, it depends on the energy you absorb the photons. For example, if you absorb a high energy photons, probably they go to S2 states. And these states will have weak binding energy. This is possible for the spin flip happens. Once this happens, so the triplet ions will, so the repulsive Coulombic reaction among these several such long-lived ions will favor a destruction of the order of a PCBM. So that's why we observe the device performance decrease a lot under the sunlight illumination. Okay. So once we understand the fluorine disorder that is contribute to the burn-in loss, so we think about if we can crystallize the PCBM in advance probably the burn-in will be slowed. So, but we cannot affect the device performance a lot. So we try to crystallize the PCBM with a middle temperature, like 85 degrees for 25 hours. Here you see the GISD image. Here we can say the PCBM diffraction arc is visible. That means the highly ordered PCBM are formed in the blend. Okay. Here, and then we go to do the stability test. Without, the lifetime is less than 1 hour. When we increase the PCBM crystalline or watering, we achieve T80 lifetime around 1,500 hours for the one-sun illumination. So another question now, how we achieve ordered PCBM nanomorphology without sacrificing the device efficiency? Okay, so the first thing, DIO is a better thing. We have to remove. Because DIO have, when you align the sample under 85 degrees for 25 hours, you will lose around 20% original efficiency with the DIO solution. And then I think about we try to replace this solution system with dichlorobenzene. So with this one, we only lose like 6% of original efficiency. Once you remove DIO, actually the performance at the beginning is quite low. It's like 7%. So that's why we modify the ratio between the PCBM and the polymer. And finally, we can achieve a similar performance as the DIO content solution. So this is good. And then we do a long-term stability test for these materials. But for the application, we have to use the UV filter to remove the UV light. Okay, so with this diagram test, more or less 2,020 hours continuous light illumination, we have around 14,000 hours lifetime, and this is equal to 7.1 years for the outdoor measurements. And if we think about a vertical application, so more than 10 years can be achieved. This is the calculation between this optimal condition and the vertical applications. So okay, let me finish my talk. So the conclusion is that PC10 PCBM absorber is intrinsically stable when oxygen or moisture eliminated. Second, burn-in these solar cells is due to a spin flip induced PCBM disorder and damage the PCBM morphology and cause the burn-in. So we try to increase the ordered PCBM phase in the blend, and then we can achieve a high efficiency and long lifetime solar cells. Okay, thank you very much.
Yeah, thank you very much. Very interesting insight. Are there any questions?
Yeah, thank you very much.
Okay.
Stand up. Okay.
It's okay.
Thanks a lot for the nice presentation and nice results. I wonder, you showed the AQE spectra to show the loss in performance for the fluorine side. So that rather points to, let's say, a generation problem, not a transport problem in a sense. So is that what you mean?
You are right.
What is happening with the spin flip? And the second question is, your procedure of creating this highly ordered PCBM regions or domains, can it be made somehow general? Because it will depend on the mixture, of course, with the polymer.
The first question is that, here, actually, the absorption spectrum doesn't change. Okay, you can see here. So this blend absorption doesn't change. And then the EQE is a change, wavelength independent, okay? So this is probably PCBM and PCB decrease a lot. So we can make a conclusion is because of the acetone diffusion in PCBM is reduced.
Okay, acetone diffusion, yeah.
And then the second one, you said, yeah, like a P3T, crystalline polymer, maybe they can fix the fusion move. Also, it's a good strategy to improve the ordering. So here, the PC10, for this material, I don't know, use other techniques, so we try to alienate. Alienate is direct effect with the PCBM. So with alienate, we can achieve ordered phase in the PCBM morphology. So I don't know you asked.
Okay.
Okay, thank you.
Okay, maybe in the interest of time, we thank the speaker again. Thank you very much.